All right. Gravity. We is gonna derive Newton's law of gravity before your very eyes. Nothing up my sleeve, my exceptionally short sleeves, that cannot be seen on this video. You had this simulation lab that you should have done by now, because you should always do your homework for the whole week on Sunday night. You should be done before you come to class. I know that everybody did that, minus people that, had deathly illness or something like fall in their life. So this will be a review, since everybody's surely done this already. All right. There's this simulation in the FET box of simulations at colorado.edu. And this simulation allows you to simulate gravitational force interactions. And you have these two stick dudes that have a rope on some big ball, and this ball, I can make it more or less massive than the other ball. But looky here, when I change the mass, notice that the forces change. And in fact, more mass, more force. Doesn't matter which mass. Can't do both at the same time. Not wired that way. More mass, more force. That means there's a direct proportionality between mass and force. In fact, the force is dependent on the mass. Because if I change the mass, the force changes. But I don't have a way to change the gravitational force unless I'm God. Okay? Or I have superpowers. I'm a mutant or Q from Star Trek, something like that. I need something different. Now the other thing is I can change the distance. And I noticed that when I increase the separation distance, so we can put this ruler up here. So at 3 meters separation distance between center of mass, there's one force. And as I make the distance larger, the force gets smaller. So force is dependent directly on mass, and force is indirectly dependent on separation distance. So just that quick set of observations that also gives me force numbers really easy, which will be important later, and it's easy to measure the meter separation distance. Oh, by the way, we also noticed that the forces are the same each time, right? Aren't those two forces the same? Forget about all the zeros, just look at the non-zero parts. Doesn't matter. Change the distance, same force. Change the mass, same force. Change the mass, same force. Change the distance, same force. So Newton's third law, poof, reciprocity, bam. Force on this equals force on that. Forces always come in pairs. All right, so verified. Of course, we could get out a Cavendish experiment apparatus that fills a whole tabletop or two. It's complicated, it's time-consuming, it's easy to mess up. We could spend 3 hours and end it frustrated that we didn't get good measurements. Hence, I ain't going to do that. All right, so there's videos of that, people doing that online. So force directly dependent on mass, force indirectly dependent on separation distance. Forces are reciprocal. They come in pairs. Okay, or I shouldn't say reciprocal, at least not a 1/over reciprocalness, just reciprocity. All right, so let's write some stuff. Force was directly dependent on mass and indirectly dependent on distance. But I had two different masses, and though you may not have noticed it, actually had two different distances. The reason I had two different distances is that the direction mattered. And since the direction mattered, that means they're vectors. There has to be a vector. If force is a vector, one of these other two inputs has to be a vector. And since mass ain't got no direction, but distances can be directed, it must be that distance is the other side of the vector. So let's just think for a minute. It's obvious that a straight line distance can be a vector because that's the whole point of a vector. It's the distance between 2 points along a straight line, and that direction means something. And the direction meant something because according to Newton, which isn't the whole story, but it's close enough, there is an attractive force between center of mass along a straight line between the center of mass. That means there's a vector, that distance, that length, that straight line length is in fact a vector. But it's a reverse-facing vector. The force that this mass here has on that mass there is pulling it back to itself, and vice versa. They're equal and opposite forces with directed distances associated with it. That's why there's two distances, not one. All right? So, since that's the case, my proportionality needs to be updated. So this is sort of unconventional, what I just did. But since I have multiple masses in direct proportionality with the single dependent force that's equal and opposite, okay, this means that my force is directly dependent on the product of those two masses and indirectly dependent on the product of the two separation distances, which are same magnitude. Okay? But I don't get to just have one distance. If I did, I wouldn't have an inverse square law, and when I went to predict things with it, it wouldn't work. It would always be wrong. Okay? Now, when I have a proportionality statement like this, with that funny little alpha symbol, fishy looking symbol, in order to bring that into the equation world, I have to bring in a constant of proportionality. Now, normally you would go F equals K times that, and that would be true. So the secret sauce, if you will, this right here is eventually going to become F equals some constant I don't know, mass 1, mass 2, over distance 1, distance 2. We're heading here. That's my expectation. Okay? We haven't delivered that expectation yet, but we expect that this proportionality, well, it must boil down to something like that. If there's a proportionality at all, it must have that structure. All right? So there's some constant that should make this true. Now, is it the big G? Yes, it's the big G, not the little g. All right. So let's think about what we got going on here. Well, remember, we figure out these dependencies, and as soon as I know that force is dependent on these other two things, then I go to town on identities. Okay? So I know that force has to equal itself, and if I wanted to, I could write force 1 on 2 equals minus force 2 on 1, but I'm not going to bother with that level of complexity. We can always bring that back in. Okay? So force is the dependent variable, and we've learned a few times now that write that identity and then multiply that dependent variable by all the fancy forms of ones that are independent. Mass, the mass can be whatever. Okay? The distance separation can be whatever. Force waits for those things before it is measured. All right. So I know that I can put fancy forms of 1 for mass and fancy forms of 1 for distance, and all I do is I preserve the identity on the dependent variable by bringing in fancy forms of 1s fancy form of 1, made out of the independent variables, some of which stand in direct proportionality and some of which stand in indirect proportionality. So what I need to do now is separate out these interaction variables. Well, M1 and M2 were interaction variables, and D1 and D2 were interaction variables. I need to collect my factors so that I have a collection of factors that represent the interaction variables, the dependencies, because that's what we're trying to model. I want a dependent equation. What are the parameters of gravity, the force of gravity? So I would write force equals force, and I'm going to bring over the D1, D2 that's over there and put them over mass 1, mass 2. And then I'm going to bring in over here M1, M2 over D1, D2. So now this right here, this chunk of the puzzle is modeling the interaction variables. So I will call these interaction variables. Now, what to call the rest of the factors? Well, remember, everything that's on the right-hand side of this equation, even after rearranging it so that my interaction variables were collected together in a group that matched the original statement of dependency, okay, I have these other pieces, leftovers. But as a whole, they preserve the identity and force. The right-hand side of the equation never stops being equivalent to force, but the way I've structured it is different than the way I started. I can't have a non-force be the right-hand side of the equation. I can rearrange its factors all I want, provided I do them legally. Not only arithmetically legally, but in accordance with the law, because the law that we stated was force is directly dependent on this and indirectly dependent on that. Okay? Well, guess what this is? This is a conversion factor pretty much every constant that you see in physics, chemistry, etc., structured this way. If you're dealing with a force law, energy law, etc., I guarantee you your constants have this structure. Because how else are you converting mass squared over distance squared to newtons? Somehow I got to get kilogram squared over meter squared to be kilogram meters per second squared. Because that's what a newton is. And newtons is the unit for force. And we started with force. Force has to equal force. It clearly equaled force. This force equaled that force. And all the dependencies are lumped into it now. All right? So this is the conversion factor. Now, if we were to back here, and we can put in, if I were to take this force value, just the 41712 newtons, it's really like a billionth of a newton or something in this form, but let's forget about that part. That force value, let's see, I'm going to try and let me scrunch that around there. So let's get back at this. So I had force equals the force value, distance 1 times distance 2 over mass 1, mass 2. And I had mass 1, mass 2 over distance 1, distance 2. Well, guess what I can do? I can read every one of those things right off the screen. Force is force, so I could, in this, this part of the puzzle right here, I can take force directly from here and pop it in there. I could figure out what this distance is, the separation distance, okay? And pop it in to both of those. The mass, poof. The other mass, bam. And I'll get a number. Then I could go into the simulation, change one or more things, recompute, and guess what's going to happen? I'm going to get the same number. It does not matter what the mass values are, what the separation distance values are. The force associated with those masses and distances in the force value times the distance squared over the product of masses will always give me, by the way, we call this G for gravity. How catchy. Big G. And since the distances in a magnitude form are the same distance, we just call it d squared or r squared, okay, for that distance. And G is always 6.7 roughly, I think it's 6.67, but who cares, times 10 to the minus 11th, and it's going to be, its units are going to be newtons, because that's what force is. Distance squared is meters squared and per kilogram squared. Well, guess what? Meter squared per kilogram squared is going to eliminate kilogram squared per meter squared, leaving you with newtons. It's a conversion factor. But it's also the structure of the force law. It's part of the structure of the force law. The main part of the structure are those interaction variables. The fact that force is directly dependent on the product of masses and indirectly dependent on the product of the distances. That's the main event. That's the interaction part of the force law. And then there's a conversion factor part of the first law. And the reason why G is a fundamental constant of the universe. And when we go to measure gravitational forces and we pay attention to mass and separation distances, we always get the same ratio. It's sort of like this is the complicated version of pi. Circumference per diameter is always the same number. Product of distances, product of mass ratios always give us the same number when in concert with the force. All right? So normally physics students don't learn of the structure of physical law until they're seniors in their physics major, and then they learn it in a much more complicated way. All right? I am telling you now, in a not nearly as yes, it's way more complicated if you decide to go down the path of being a physicist. All right, but the understanding isn't here. Other thing also, everybody likes to make a big deal about Newton's law of gravity. It's an inverse square law, and why is it inverse square? Why is it inverse cube or inverse something else? Well, it's inverse square because it has to be, because I have the product of vector distances in its denominator. It must be inverse square because that's the nature of the relationship. It can't be anything else. Now here's the funny thing is if you were to go grab a bunch of data, and we'll do this again when we do Coulomb's law in second semester because it has the exact same structure. Instead of mass it's charge, and instead of big G it's little k for Coulomb constant. Okay? The reason why Coulomb's name is spelled with a C, capital C for Coulomb, we use little k for Coulomb's constant, and the reason we do that is because he was the original lowrider. And get it? You know how they spell K? Those booming stereo cars that we were talking about the other day? It's cool. Oh, guys, after lunch, you guys got to wake up. All right, more on that later. So that's the law. We just built it. The gravity law, formally stated, would be, now this is in magnitude right now. I'll fix that in a second. the gravitational force will be Newton's constant, big G, product of masses over distance squared. Now this is a magnitude only equation at the moment. If I bring in the unit vector for separation distance, then I get a vector equation. So this right here, this is the magnitude part. And this right here is the direction part. Vectors are always a product of magnitude and direction. And so if I know the position vector or that distance displacement vector for the distance separation, divide it by its magnitude, poof, I have a unit vector for that. All right, so that's that Newton's law built up. Your simulation lab is supposed to not only get you to do this, but also have you show by comparing two sets of mass distance data that you keep getting G. Okay. Now, of course, you're going to get it because the simulation is written on this law as you see it. G is built into it. Therefore, the forces are guaranteed to give you the right answer based on those distances. Okay. But something like a Cavendish experiment basically had two different size metal balls that were on an apparatus where very sensitive torque measurements would let you recognize that there's a gravitational interaction between those two objects. Okay, but it's a complicated gadget, and takes a fair amount of time to get it to cooperate. So there's that. So that's the gravity law. Now, before we get into building visual Python orbits and stuff like that, let's see here. I need me a circle. Guess that'll work for a circle. Circles have a center. I'm gonna make this a big center. So this would be some sort of mass, like this could be the Earth or something. And out at some radius r, we could have some much smaller thing that so let's make this even more interesting. So that's an exceptionally large, so that could be like the Moon-Earth orbit. Or it could be an oversized satellite so we can see it in our thing. And this thing is going in a circular path, okay? So it has some speed tangent to the path. Let's try that again. Okay, so that's perpendicular. So it's got some speed here. And I think you know by now that for something to stay in orbit, it's got to maintain a speed tangent to the circular path that keeps it on that circular path, because something else is accelerating it towards the center. So if you think back to the circular motion lecture that I had you take notes on from video, now we're going to start to use that here and expand that later on when we get to more complicated rotational motion. But this is circular motion. Rotational motion, circular motion, not the same thing. Rotational motion more about something on a fixed axis, like a disk rotating. This is circular motion. This is something moving in a circular path, a single particle or something modeled as a single particle. So you could think about a ball on a rope and you're swinging it around. Why does the ball take a circular path? Well, by slinging that thing around, you're providing a speed to that ball, but the rope keeps pulling it to the middle. So it's easy to see why, if you were to watch it from above, or if you could see it tracing out a path, it would be a circular path because of that rope. It's a fixed radius, it's stuck there, it's moving around, it can't, unless it breaks free, it's not going to break free, and the only reason that it stops the circular path is you give it less and less, and eventually it falls out of its circular path. So satellites, be they man-made satellites or God-made satellites, moons, comets, stars. You know that our solar system is, anybody know how long it takes to go around the galaxy? How many years? It's like 250 million years. Our galaxy is 100 billion light years. I'm sorry, 100,000 light years across. So if you want to go from one side to the other, across the diameter of our galaxy, you would need 100,000 years at the speed of light. Average time distance between galaxies is 10 million years. 10 million light years. On average. Now, we have a couple that are closer, like Andromeda, you can do it in 2. But on average, 10 million years to hop galaxies. So if you're planning a vacation, summer vacation, factor that in, okay? Let your boss know. I'll be gone for 10 million years. Anyways, meanwhile, back at the ranch. So you have moons going around their planets. You have planets and their moons going around their stars. You have stars going around the center of galaxies that's filled with black holes and whatnot. It's a complicated mess, and all of that is moving through empty space. So the solar system has an orbital velocity, while all of its parts have orbital velocities therein. It's an interesting, complicated, hot mess. All right. Anyways, so I have this speed, and we found that this center-seeking acceleration, centripetal acceleration, was v squared over r. So when the motion is circular motion, the acceleration is v squared over r as opposed to delta v over delta t. Delta v over delta t works along a straight line. If the path is a straight line, or parts of it are, then delta v per delta t. But if any part of the path is circular, meaning there's a constant radius of curvature, then that part of the path, acceleration is this way. Because the acceleration, if the path is circular, that means something's always drawing it to the center of the circle. Centripetal acceleration, this v squared over r business, is center-seeking acceleration. So every orbital thing is trying to seek the center of that circular path, but it has a speed tangent to that path that's just enough to keep it on the path. It's not too much to get it off the path, and it's not too little to let it fall into the thing it's orbiting. Okay? So there is this Goldilocks zone of speeds that keeps something in circular orbit, or perhaps even elliptical orbits. Most orbits aren't purely circle. Most of them are elliptical. All right? We have some circular orbits for things like satellites and whatnot, but everything else is pretty much an elliptical orbit. So we have that. Well, if I were to sum the forces here, sum of forces, it always equals ma. That's the general equation. That's Newton's second law. It basically applies everywhere. For all intents and purposes. It's universally true. Okay? But there are places in the universe that are weird. Quantum world's weird, so that's why I essentially universal. Okay? Well, we like to call this the net force. And I'm doing this on purpose because it's what we're going to do when we write code. And so for this particular situation, all right, it's MAC because this right here, this is a center-seeking acceleration. It's keeping it on the circular path, and it's constant. And that's what you would expect, because guess what the force of gravity is going to be at a constant separation distance? It's going to be one value. And the only way it would change is if the mass of the system changes or the separation distance changes, or both. But if the mass of the planet and its satellite don't change and the separation distance don't change, then you don't need to change speed. Okay, it'll maintain that thing. So guess what we have here? We just figured out that the net force, well, is there any force on the orbiting thing other than gravity? It's out in space, no friction. We're ignoring electrical forces. There's no other force in our system except the gravitational force. So the net force would be big G. And if this is little m here, then I'll have little m times big M over r squared will equal little m times v squared over r. Well, interestingly enough, the mass of the orbiting thing is irrelevant in this force balance. Don't need radius on one side. So we easily obtain that v squared is big G, big M over r, which means the orbital speed that maintains that radius is the square root of Newton's constant over the mass of the body that's providing the center-seeking acceleration, and that value, that separation distance that I want to keep constant. So this orbital speed equation applies to anything trying to orbit anything, because Newton's big G constant applies everywhere in the universe. The big mass is the mass of the thing you're orbiting, and the radius is the distance at which you intend to orbit. Okay? So we can compute the orbital speed required to keep something on a circular path. Meaning this is the speed, the linear speed tangent to the circular path that you want, that you must maintain. So the thrusters need to be at this level to have this speed so that I stay on this path, which is at this radius. All right? That's what we have right here. So we built Newton's law of gravity, and now we've extended what centripetal acceleration was in our general approach to circular motion. Now it's been applied directly to circular motion, Newton's second law, Newton's law of gravity. That's what we just done did. All right.